Bien, rebonjour à toutes et à tous. C'est un plaisir d'accueillir Benoît Vermersch dans ce séminaire. Il va parler en anglais, mais je l'introduis en français quand même, parce qu'il est français. Benoît est théoricien, spécialiste de la physique quantique à ENCOR, de l'informatique quantique, des technologies quantiques, tout ce qui est quantique en ce moment. Il est maître de conférence à l'Université de Grenoble et également détaché depuis un an et demi, m'a-t-il dit, dans une start-up, Quobly, qui est une start-up à Grenoble, qui vise à produire des processeurs quantiques. Alors Benoît et moi, on se connaît depuis un certain temps, 15 ans, je crois, au moins, peut-être même un peu plus. Ouais. Notre rencontre, elle date de l'époque où il était élève dans une grande école du plateau de Palaiseau. Je vous laisse deviner laquelle. Il devait subir mes cours là-bas, mais il n'est pas rancunier, hein, il est revenu aujourd'hui. Voilà. Donc, il est ensuite parti pour Lille pour une thèse dans le groupe de Jean-Claude Garot, thèse qu'il a soutenue en 2013. Et ensuite, il a fait un très long postdoc. Alors, ce n'était pas d'ailleurs toujours un postdoc, c'était aussi assistant de professeur là-bas. C'était avec Peter Zoller à Innsbruck. Et on a collaboré pas mal ensemble à ce moment-là, parce qu'on avait une bourse RC Synergie. Donc, nos différents groupes se voyaient très fréquemment pendant 6 ans. Ça a été un grand plaisir. Alors, Benoît a ensuite rejoint Grenoble en 2019, et donc il y est toujours. Il a fait beaucoup de contributions importantes à ce domaine frontière entre la physique quantique à ENCOR et puis l'information quantique. L'idée générale, enfin tu m'arrêtes si je me trompe, c'est de partir des concepts vraiment de l'information quantique pour faire des outils qui sont utiles pour faire des processeurs après. Alors, je ne vais pas citer toutes ces contributions, hein, mais je peux mentionner l'idée de mesures randomisées. C'est du franglais peut-être, mais enfin bon, c'est passé dans le langage commun. Les mesures randomisées pour les processeurs quantiques et les futurs ordinateurs quantiques, de la dynamique non markovienne dans des réseaux de spin, ou encore, et c'est vraiment en lien avec ce que tu vas nous décrire aujourd'hui, la caractérisation expérimentale de systèmes quantiques à plusieurs corps. Donc je suis vraiment très heureux de te laisser la parole et que nous expliques ce que c'est cet effet Mpemba, classique ou quantique.
Merci Jean. So, good morning everyone, and first I would like to thank Jean for a kind invitation. It's a great honor to be here and to speak after you, after all these times we met together when I was in Innsbruck, and I had to travel with my Austrian colleagues to Paris and tell them about RER and all these things. So as you said, I'm more of a quantum type. I like quantum physics very much, and I'm not so comfortable with classical physics in general, in terms of my research life, of course. But for today, I will discuss about connections between classical mechanics and quantum mechanics in the context of this quantum Mpemba effect. And in my case, it was really the possibility to observe this phenomena which gave me the motivation to study that. So I will try to go back and forth between experimental world and theory world to explain how this debate and controversy about Mpemba effect emerged, and how, in particular, from a theory description of the classical Mpemba effect, some people could propose the quantum Mpemba effect and then observe it experimentally. So first I want to thank some of my long-term collaborators. So as Jean said, I was for a very long time postdoc in Innsbruck in the group of Peter Zoller. He's a person who pushed me to try to discuss with experimentalists. Sometimes it's not so easy because they have many they have incredible results, and then as a young theorist you are trying to explain what looks like half-baked idea sometimes, and with Peter it was made easy because of his long experience and insightful advice. And I had the chance also to interact at this time with Ignacio Sirac, and as you may know, Peter and Ignacio have several fundamental works on quantum information, and it was really great to work with these two persons. And Andreas, who, as you can see in between, is now a close friend and collaborator who was in Innsbruck at the same time. I will also discuss works based on working with my students in Grenoble, in particular Aniket, who was my first PhD student in Grenoble during COVID time. And I also want to thank the experimentalists in Innsbruck, the group of Rainer Blatt and Christian Roos, and Manoj was the postdoc in charge of the experiment. So with this team, we had a very good time because we were in the same building, theory and experiment, and we had a lot of fun. So what's the menu for today? First, I will describe classical Mpemba effects with not so many equations. It's more to give you the context of what this effect is, what is controversial about it. It gives also, I think, a good example of how scientific discoveries are led by experimental measurements, and in particular, the question of reproducibility will be studied. And I will conclude this part with a toy model for the classical Mpemba effect, which I like very much, because it's simple enough to give you some intuition, and the equation that you will see will be connected to quantum mechanics, just the equation, not the microscopic system. So this will be my transition to the quantum system, quantum information, kind of a short tutorial about quantum information, just what I need. In parallel with experimental platforms, so how they look like and how I can write a wave function and a Hamiltonian for the system. And finally, a conclusion about this observation of a quantum Mpemba effect. So Erasto Mpemba was he was a student or a pupil in Tanzania. He was 13 when he discovered this effect. He discovered this classical Mpemba effect on his own. Okay, it was not in the context of a school project. And this discovery became public when a professor from UK, Osborne, visited his school and gave a lecture about, I think it was a general lecture about physics. And then there was a moment for questions, like ask me anything. And this Mpemba asked these very good, very nicely formulated questions. Like it looks like it comes suddenly. You take 2 beakers of equal volumes of water, one at 35 degrees Celsius. I will consider that this is cold in the next slide, and the other one, which is hot, at 100 degrees Celsius. You put them in a freezer. The one that started at 100 degrees Celsius freezes first. So it's affirmation that this is what happens. And now I ask the theorist or the world to explain. Okay. And I think it's quite remarkable at this age to formulate a physics problem like that. And the story is that he made this discovery not with water but with ice cream, which is a very different material. He used to make ice cream from milk. He used to boil the milk. I'm not sure why. Anyway, so he would boil milk. He would put other ingredients, I hope. And then usually it would make sense to wait a bit before you put this mixture into the freezer, because you don't want to heat up everything in your freezer, for example. So he would wait usually. But one day he was in a rush, and then he put the hot milk directly into the freezer, and he realized he could enjoy his ice cream before his schoolmates. So this was immediately useful, so to say. And I'm not sure why he asked the question with water. Perhaps he thought the experiment would be easier, but actually it's not the case, as we will see. Okay, so that's the story behind the discovery of Mpemba effect with water and with ice cream. So Osborne had a nice reaction. He said, today I cannot explain. He didn't say it sounds wrong, he'd say I cannot explain. Let's do the experiment together and then we will see. And then they wrote a paper together. The paper you can find online here. This is the plot that you can find in the paper. The paper is very nicely written. And this is really the claim of the Mpemba effect. If you have a temperature which is high, the time to freeze is lower compared to when you start from initial temperature which is low. Okay. Now it's time to explain, and it's difficult to explain or even to agree with the effect. First of all, there's a little bit of controversy on the definition of Mpemba effect. Do we have Mpemba effect when we record the time when the water starts freezing or stops freezing? That's the first question. It's actually non-trivial, because some experiments did the experiment with the first criterion, some others with the second one. Can you also use a thermometer to detect quantum Mpemba effect? It would mean that you associate freezing with the fact that the temperature is 0. But we know it's not always like that in real life. Water can freeze at a temperature which is below 0 degree due to complicated chemistry processes, and it's called supercooling. I will mention that very soon. Okay. So first problem is how to define a proper Mpemba effect in terms of what do you mean by that. And second is equally important is how do you perform such an experiment and how you make it reproducible. So if you look at the papers, I have looked at some of them, not all of them. It is really written, we tried this option, sometimes we see the Mpemba effect, sometimes we don't see it, so it's not an easy experiment. You can even look at YouTube videos where people try in their garage or outside, and very often doesn't work, actually. So it has been argued that this problem may come from the container. Maybe the Mpemba effect arises from some impurities in the water when you first try, or by actually the shape of it, how you connect this water to the environment, so the interface. I have also seen about the location of a thermometer. So this I cannot say much. And overall, the problem is hard experimentally. It's perhaps harder experimentally than on the theory side to observe this effect. And we have the word controversy in all this, in all the internet about a classical Mpemba effect, but it's a healthy controversy. So people argue, but with reasonable arguments. So I would say it's fine, and it's a good example of how we make science with different backgrounds and experimental platform. That's what I want to say. So now I give some explanations based on the assumption that the effect exists. Okay. So the first thing we can say is that definitely this effect is related to non-equilibrium physics. If I would assume that we are dealing with equilibrium physics, what I mean by that is that at any time of the cooling process, the state of water in this case is described by a temperature. So at each increment of time, you could assume that your water is at a given temperature, and if you give me the temperature, I know in which shade it is. It's one-to-one the same thing. If it's like that, if I start from water which is initially hot, what can happen for the state and thus for the temperature is that, of course, the temperature will go down because it's getting cold in the freezer. At some point, the temperature will reach the one associated with the other container with cold water. And at this time, I'm exactly in the same initial conditions for my physical experiment. So what can happen next is the exact same thing that happened to the water which is initially cold. It's just I reset time. And therefore, the hot water will freeze afterwards because it will never catch up what happened to the cold water. Okay? It's fine. So we know that many physical phenomena are related to non-equilibrium physics. It's just to set the context. Second thing I can say is now more precise, is that perhaps what happens with the hot water is that it's very hot, okay, and you are maybe too slow when you walk towards the freezer, and when you are walking, some water will evaporate, and then when you will put this water into a freezer, and you have just less water to freeze, and then you can hope that it will take less time. Okay. Personally, I don't buy it at all, but the arguments are somehow logic. They don't contradict each other. One explanation, which is perhaps the most accepted, is supercooling, and now we are dealing with thermodynamics. So as I said, supercooling is a process where the freezing will start below 0 degrees. So you would start from positive temperature, reach 0, nothing happens, you go a little bit below 0, and at some point it will freeze, and it's not so clear at which time it will freeze and under which conditions. And indeed, the process of freezing, so of building ice from liquid water, is initially triggered by a crystalline seed. So ice is a crystal. You need to build this crystal from somewhere. This somewhere and the condition from this somewhere to exist is a matter of chemistry. We have hydrogen bonds which play a role in all this, and impurities and all of that. But the claim is, and this is a claim in this paper, is that if you start from cold water, you start somehow from water which is already cold, as I said. So you can imagine the process to be gentle enough so that you will cool slowly, so gently that you will go at 0 and then continue and supercool. And so you will have supercooling for the cold water, while the hot water process will be kind of more brutal, and then you can hope that this provides an explanation. The hot water will not supercool that much compared to the cold water. But that's the explanation. Also makes sense. Difficult to prove for water. Okay, so the debate is really going on. So you can look at the internet. It's quite fascinating. Now, I talked about water, but initially the effect was for ice. So people have also now returned to other materials because water is eventually too complicated. So let's try to see if we can think of Mpemba effect elsewhere. In particular, in materials where we don't have to deal with the phase transition, like freezing. It has been observed or predicted by numerical simulations in many materials. And this was useful on the theory side because these materials or associated with theory models which are simpler to understand. Okay. And this is where I want to come to. And there was this seminal paper that I quote here. It's from 2017, so quite recently. And this had a lot of impact also in the news, because there is a nice toy model to explain the classical Mpemba effect. So finally, we can try to understand some of it. So what's the model? It's a classical model where you have a particle which can hop between 3 sites, 1, 2, 3. And it hops with some probabilities or some rates which are given in this figure. So if you are here in 3, the rate to go from 3 to 1 is R13, and you have the reverse process. And these rates follow some constraints due to the fact that you want to have a probability distribution which is conserved. And you define this model stochastically. So you will define the probability to be in one of these spots or the other. And stochasticity or randomness comes from the fact that you will repeat this experiment many times, and you want to describe the average of the probability to be in a given site. Okay? So that's classical, fully classical. The state is described by probability P1, P2, P3 to be in 1, 2, 3. The sum of these 3 numbers is equal to 1. And then I'm a theorist, so I can just propose an equation, adopt an equation to proceed with. And in this case, with all these rates, the equation is called a Markovian master equation. And it's very simple. The time evolution of probability P is given by the derivative equal a linear operator L times P. So that's really the same, it's equivalent to speaking about rates. And it's called Markovian master equations because what happens next to a system in the future, so what happens on the left, is dictated by the present, P of t. So it's a time local equations. This is the type of equations we like in quantum mechanics, and I will talk a lot about this form in the future. And it's probably not good enough for water. Okay, so that's why it's a toy model, but at least I can work with it. P is a vector of length 3. The same for the derivative, so the L is a 3 by 3 matrix, and it is symmetric based on the formalism. Because it's symmetric, I can diagonalize it, as in quantum mechanics. I will find 3 eigenvectors, v1, v2, v3, 3 eigenvalues. I can order them. Something I cannot show today is that one of these eigenvalues is equal to 0, and you can also show that it's the largest one, so the other ones are negative. The fact that you have one eigenvalue which is 0 implies that there is a steady state. So in any case, P of t after some time will reach a plateau value, and that's the equivalent of being frozen for what I said earlier. It's the steady state. And the question is how you approach the steady state and how we can define Mpemba there. And the approach is given by the time dependence of the 2 other modes. We talk about modes here for the eigenvectors. The lambda 2 and the lambda 3 are in particular different. So I can write this general equation here. If I plug P of t here, I get a match. So that's the solution. Lambda 2 is larger than lambda 3, negative. So at the long time, this term will dominate against this one. So because this term will dominate at long time, I call this mode the slow mode. It's the one which is slow to converge. Okay, and that's my turtle, right? And that's the rabbit. Okay, so everything is about long times and how you couple to the slow mode to understand what happens in the Mpemba effect for the toy model. And what are the conditions not to observe the Mpemba effect in this toy model is simply you would take an initial state which is hot, and by hot I mean it's very far as possible from the steady state. That's what I mean by hot in this toy model. The hot state is far from the steady state, and at the same time, it has a slow overlap with the slow mode. So initially, it's always of this type, but initially, everything is specified by the A2 and the A3, which are parameterized by the initial conditions. For the hot state, I want like a rabbit, I want A3 to be large. And for the cold state, it's the opposite. I want to be kind of close to steady state, but I want to match the second mode. Okay. And there, it makes sense. Finally, Mpemba effect is intuitive for a toy model. You just need to find states which are fast to relax. Okay. It's almost trivial here. But if you read the news, again, the internet, broad audience journals, this corresponds to what you see in the explanation sometimes. You say, perhaps the initial hot states, they are able to find shortcuts towards equilibrium. So that's what they mean. They mean there is a mode which is kind of slow to relax. The hot state is not of this type. And when they... yeah, that's what I want to say about the toy model. A few years after, there was an experiment showing an analogy, a model, the realization of a model which is close to the toy model, classical physics, of course, with colloids. So colloids is a system where you have particles, microscopic particles, in a liquid, and you can typically observe these particles, which can be resolved with imaging techniques. And instead of using a thermometer, you just image the particles, and then when you see that the particles reach a steady state, a steady distribution, you declare the state to be thermal. And you can also quantify all that. And you see an ambiguous, reproducible, classical Mpemba effect in this system, which is not water, but which is still remarkable. I don't know if you knew, Jean, about this experiment. It was made with optical tweezer techniques, so you are the expert, right? And it was made with very fancy optical tweezer techniques, like they call the fake traps and something like that. Perhaps let's discuss this someday. But I thought about you when I read about optical tweezer traps. So now I want to switch to the quantum world, and I will justify this in two ways. First is about theory, because the equations that I saw and that many other quantum physicists saw is this one, and this one is very analogous to the kind of equations we are dealing with in quantum mechanics. So it's very little effort for the theorists to see and try, because they kind of know this equation very well. Second theory reason is that perhaps we can have a safe discussion about quantum Mpemba effect in quantum mechanics, because sometimes in quantum mechanics it's easier to specify the conditions for an experiment. We are dealing with typically a small number of particles. It's not always the case, as we have seen with Jean. But sometimes we have a small number of particles, and you can specify everything with typically a Hamiltonian. and then you agree or not, but the conditions are kind of, in my opinion, maybe I'm biased, easier to specify, and we should allow for a good reproducibility of the Mpemba effect. Second motivation, which comes more from my background, is that we have already the tools to observe thermalization of quantum systems in many experiments. It's something which is possible with the rise of quantum computers. But I will show you images where you really see a quantum system thermalizing quantitatively based on measuring some important physical quantities. And it's about the good time to study quantum Mpemba effect, because these tools are now available and have been available for a few years. And therefore, how to put it, the quantum Mpemba effect is a good validation of all these techniques that were developed to prepare and measure quantum states. So that's why I was convinced also by this experiment. Okay, so now I need to take a step back, so I will not talk about Mpemba for a few slides, because I need to define the quantum systems and what I want to measure in the end, and how I want to define the Mpemba effect. Okay, so I will consider a very generic quantum system. In my case, this will be atoms or electrons. So you can think of these blue circles to be individual quantum particles. So it can be one atom here, one atom there, one atom there, and so on. In contrast to Jean, typically my atoms are distinguishable, so I can really address this one, and then this one, and then this one. This will give me an exponentially large Hilbert space, which will be useful. And I can define a system. The system is just a bunch of particles, here these four, and I can define other particles to act as the freezer, so as the environment which will affect the system of interest. Okay, so this is the setup. All these particles are coupled and described by the Schrödinger equation, which is written here, with H is the Hamiltonian of the system, which gives me the physics. So what is important for me is that it's not that I can study A and B separately, of course. Hamiltonian H typically couples A to B. And as a result of that, because they are coupling terms, the state psi is said to be entangled. And the definition of entangled is the following: the wave function psi cannot be written as a tensor product of the two wave functions. And that's very, very important to study quantum thermalization. Quantum thermalization comes from the fact that there will be a non-trivial interactions between A and B. And this will give rise to entropy production and all what you need for describing a thermodynamic limit, a thermodynamic ensemble. So why do I care about entanglement? So entanglement, first, is a resource in quantum computing. It's what you need to have a quantum computer or a quantum simulator, which is a similar object. You can show that in the absence of entanglement, a quantum computer is no more powerful than a classical computer. It doesn't mean entanglement gives you everything or computes everything, but it's a necessary ingredient for having something powerful. That's why we care. Because of that, over the years, and in particular in Innsbruck, there was a lot of work going on to try to produce this entangled state and verify that you are able to create this entangled state. Because if you can prove that you have an entangled state, then you can prove there is hope for quantum computing. Mm-hmm. Now back to thermalization. So thermalization, it's the same system, it's just a different viewpoint. I'm looking at A, and I'm trying to see how B will thermalize, will help A to thermalize, so to say. and I know that the mechanism behind it is entanglement. Okay. So entanglement in this talk plays an important role, and for us this was a motivation to study this effect. Now this was a conceptual statement. Now I'm back to experiments. I want to explain how you can create entanglement, entangled state in an experiment. Okay. So I will focus on the trapped ion system. So here it's an image of individual ions. So these are calcium ions, and they are trapped in this device via electrodes. And what you see is really the picture of an individual quantum particle. These particles are separated by a few microns, and this gives us the possibilities to image and address and measure all these quantum particles individually. In particular, you can address two electronic levels and form a two-level system, as we have seen in the lecture by Jean. In my case, I will be considering these two states. One is a ground state, and one is so-called a clock state. It's a state with a very long lifetime. And these two states are both long-lived. I can perform many quantum operations before decoherence kicks in. Okay. So that's my two-level system, and I have several of them right next to each other. The rotation is made by a laser, so it has the right frequency to compensate the energy offset. And I can also image the atoms, so I can shine light on the ion, for the purpose of knowing in which quantum state I am. And therefore, I realize a quantum projective measurement which tells me if I am in a quantum state or not. It's been done in this example. This is how I get this image. Okay. I shine light. The light is re-emitted in all possible directions by fluorescence, and when I collect this light, I can know with extremely high probability if I am spin up or spin down. What is the system behind it? Now, these ions will interact, so this collection of two-level system will interact via Hamiltonian, via the Schrödinger equation. And the Hamiltonian, I write it here. I will not derive it, but it comes from the Coulomb interaction and some complex quantum optic process. And in the perturbative regime, we obtain this expression, which I just accept for a moment. This Hamiltonian is a sum over all ions, so I and J are ion indices. There comes a prefactor, so a coupling strength, and there comes the operator in a second quantization form. It's very similar to your A and B operators, but somehow in a different context. What the sigma J minus does, it takes an excitation of spin up on ion J and then put it to spin down. And sigma I plus is the raising operator. It takes spin down and maps it to spin up. So that's an example. If you apply H to up, down, 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 you get down, up, down, down, down. Okay. And in general, by applying this Hamiltonian H for a finite amount of time, you will create exponentially many basis states of this type. So you have the state is one spin configuration plus the other one, plus the other one, plus the other one, and you have 2 to the power n such possibilities. So that's very rich dynamics, sometimes very complex. And this is really the mechanism behind the quantum computer. We are able to create entangled quantum states on demand, and we know exactly what we are doing up to errors that we can later correct, and that's a story for another day. But I just want to say that the Nobel Prize in physics was given to David Wanland at NIST for demonstration of this kind of mechanism with 1 and 2 ions, exactly the same year as Serge Roche demonstrating similar level of quantum control of individual particles with Rydberg state and microwave photons. Okay. That's the story of this Nobel Prize, being able to address and measure individual quantum particles. So now that I motivated the experimental system, I come back to quantum info, and then I want to define what I need to measure to understand quantum dynamics. So as I said, I'm interested in A, and actually I'm only interested in A. I just want now to avoid dealing with what happens in B. It's too complex. I just want to focus on A. Will this formalize or not? And in this case, the wave function of the total system is too much for me. I can just focus on the so-called reduced density matrix. It's a mathematical object which you build from the wave function, and you apply a linear operation on it, which has the purpose of erasing the information which is in B. So it's a little bit mysterious what I say with these equations. Let me just tell you how this was introduced. The density matrix is an object which was introduced to be able to compute all expectations values having support in the system A. So let's say if I want to know the number of spin up and spin down, or the difference or the variance of this operator, all of that, there is a quantity which I can use to calculate that. It's based on this equation. Expectation values of OA is equal to trace of OA times rho A. That's what I demand for a density matrix. I can calculate all physical properties of A. If you impose that, you get this expression here. And if you satisfy that, you can claim that the density matrix in A is the quantum state. There is nothing more that you can know about the state that compared to what is contained in the density matrix. So that is statement number 1. I can study quantum state dynamics looking at this object, which is the density matrix. And all textbooks in quantum info are about density matrices, or how much you can extract or encode or distribute. All of that is about density matrices, so that's tool number 1 in our field. You can describe entanglement, but I have no time to discuss that today. But trust me, entanglement and density matrices are very much related. And now I'm ready to discuss thermalization, finally, after all these steps. I will describe thermalization as the trajectory of the density matrix as a function of time. I want to study if the density matrix, how it evolves, does it evolve faster compared to slower in different conditions. That's the topic of quantum thermalization. And there are a few things I can say. Generically, if B is large enough, we will see that the density matrix reaches a steady state. It will not oscillate forever, as you have typically with a wave function with a small number of degrees of freedom. So in your case, Jean, to reach a steady state, you had to add many particles. If you would have stopped at 2, no steady state, right? So I can achieve the same thing with the density matrix, and because of the same microscopic ingredient, which is having a large environment. We can define temperature based on the steady state density matrix. It exists, I just want to mention it, but I don't need it for this talk. You can also define different type of thermalization. You have closed system thermalization. It's when you have the system B, which is made of individual particles that you kind of know and you can model in your Hamiltonian description, or you can have B to be a continuum of quantum particles. So you can think of photons in free space, and in this case, you think about open quantum system. So now I show an example of thermalization for one atom. So that's just an example. The object I want to thermalize is one atom. It's one dot here, A. It will be thermalized by B, which is made of photonic modes. So it's just, I put the atom in free space. And I know that there will be a probability to have spontaneous emission. The Hamiltonian will be described by this one. This term is the same as we have seen this morning. It corresponds to the fact that my two energy levels are separated by omega 0, and here I forgot the h bar. I have a classical drive, so I can shine light in a coherent manner to drive transition between the two levels. We have seen also this term this morning. This was the AB term. And the new term is coupling to the environment, which I can write in second quantization in this form. I have a dispersion relation for my photons and a light matter coupling with this sum over there. It's typically the sum of k will be infinite, so it's difficult to solve. I think it's impossible in the general regime. But what I can do, now I can make an approximation, which is called the Born-Markov approximation. I would assume that the coupling G is weak compared to the sum of energy scale which are there. And I will assume I will assume something else related to the so-called memory of the environment. This is very technical, and it's taught in quantum optics lecture. I ask you to accept it for a moment. And I claim that I obtain this equation for the density matrix, which is a so-called Lindblad equations. Time derivative of a density matrix is equal to a linear operator times rho A. So that's, remember, I had before the Markov equations for the toy model. That's the analogy for quantum mechanics. Quantum state can relax very often with an equation of this type, which is the Lindblad equation. And the gamma here is called the relaxation rate. It's a function, it's a complicated function of coupling rates to the environment. And HS is this part. And then you can solve this equation numerically, because it's a 2x2 matrix in this case, and you can solve, you can see what happens to the state, and you have some oscillations. This is due to omega, and you have some relaxations due to gamma. Okay, and yeah, so actually Jean proposed a method to solve these equations back in '93. Yeah. So you 92, you were, I think, the first to propose an efficient method to solve these equations for large systems. If you have many particles, this matrix is of dimension 2 to the n times 2 to the n, and you propose to reduce the memory usage to 2 to the n if we speak in this language. Yeah. So thanks for that. And now I'm ready to define the Mpemba effect, because I have at the same time the notion of quantum states, the notion of evolution of quantum states with an equations I can write down. And I can see that quantum states do reach a steady state, so I can think of thermalization by defining thermalization as the process of reaching a steady state. And therefore, I can conclude by proposing a definition of a Mpemba effect. Sorry, it's my voicemail. So let's propose a definition. It was not for me, obviously, of the quantum Mpemba effect. It would be the fact that I consider two initial states. One I will call the hot initial state, and the other one I will call the cold initial state. And they are defined from the fact that the distance of the hot initial state to the steady state is larger than the distance of the cold initial state to its steady state. And in general, rho h and steady state and rho cold steady states can be different. On this graph, it looks like that. The hot state is above the cold state. And the question I'm asking is there a crossing in this curve? So does the distance to the steady state goes faster to 0 when I start from the initial state? That's the one-to-one Mpemba in action. And people have worked on it, and in my case, I want to, there are many works, starting from the 19th. I will talk specifically on the works by the CISA team from Trieste, from Filiberto, Sarah, and Pasquale, who were all in Trieste at this point. And you can see that they were in Trieste because they always take pictures with a blackboard behind, and we put formulas behind. So that's how you recognize CISA. And Pasquale is an expert on statistical physics, quantum thermalizations, and critical systems. And then there were some experiments. And the first two experiments were done in 2024, back to back. You can see the journal numbers are the same, +1. And there was a physics article about it. Okay, and one year after, there was another experiment. So I will talk about this one. So a lot of credit should go to Lata. She was a postdoc with me in Innsbruck, and then she joined Trieste. You can see the blackboard. And Aniket, he was a PhD student with me in Grenoble. So I think he wanted to do the same, so he put a picture with a whiteboard, because this is what we have in Grenoble. But with interesting photonic modes in between. And Manosh is more connected to real life. He put a picture with the mountains in Innsbruck. He's the experimentalist. So I think it's perfect. I have maybe 5 minutes to explain the experiment. So I try to convince you that the density matrix is the object we want to measure in an experiment to study thermalization. And I also said many slides ago that we can measure the ions being in spin up and spin down. Unfortunately, if you just measure spin up or spin down and you do this many times, you don't have a density matrix. You only see the diagonal part of the density matrix. You only see probabilities to be in a certain state. To reconstruct the density matrix, or more efficiently to reconstruct physical properties associated with the density matrix, you need to do what is called randomized measurements. You create a quantum system. So here you have an image of 20 ions. And before you measure, you will rotate the state U1, U2, U3 with unitary matrices, single qubit rotations, by an amount which you know. Okay, and this maps the state on the Bohr sphere from one angle to the other, as we have seen in Jean's lecture. In our case, we like to do it randomly. It's just a detail, but we take some U, we get some data, then we change the U, and we do it over and over. And that's the method we developed in Innsbruck. And in particular, what we can do, we can measure distance between quantum states. And this is really only possible in quantum computers and related devices. So if I want to study thermalization, I want to study a distance between two quantum states. I want a quantity which is 0 if and only if the states are the same. If ρ1 equals ρ2, so that's a quantum state distance. In order to do that, what I can do, I can take the two quantum states separately, in parallel. I can apply the same random operations and then followed by a measurement. And what we showed is that if you take this U to be equally the same, but taken randomly over many many runs, from the statistics of these two objects, you can relate to the quantum state distance quantitatively. And intuitively, it's not so much a surprise. If the two states are the same, the statistics should be the same, and if they are different, they should be different. What was nice is to be able to write down a formula to quantify the relation between these two objects. Then credit should go to Trieste. What they found is that if you measure this distance, you will see the Mpemba effect for trapped ions. So they took a model of this type, a flip-flop interaction model. They defined a family of initial state to define the hot and the cold initial state. They define it with rotation on the Bloch sphere, actually, along the y-axis. And they also defined a criterion, which is called the entanglement asymmetry. Very nice, but today we'll discuss for simplicity just the distance that I introduced here. And then summing up, the experimentalists did this time sequence, so that's a time axis, and that's the ions, so that's an image of a quantum circuit. You take all the ions down, you generate the hot and the cold initial state with this building block, you let the system evolve, you measure with randomized measurements, you do this many times, and then you make your statement. And experimentally, and also for Aniket, who did the analysis with LATA, this was routine work. So we have done this kind of experimental sequence many times. We just didn't know that there was an Mpemba effect. But it was, for them, it was really business as usual. And then you see the Mpemba effect here. Crossing, okay, so the curve crosses. Frobenius distance here. The triangle is the hot initial state. It relaxes faster than the green circle, for example, the cold initial state. That was too fast. And what was also nice is when we uploaded the paper, there was an interpretation of the Mpemba effect which appeared the exact same day from Trieste again and co-workers. And in a nutshell, but it's kind of complicated, but in a nutshell, what they did is they could bring an analogy between the toy model, which I explained at the beginning of this talk with the slow modes, fast modes, and these systems. And what happens is when you have a quantum systems with this type of model, and if you make further assumptions on this model, you can describe thermalization in the following way. You have your initial state. You can think of your initial state is the thermal state plus excitations on top. And then you can write an equation for these excitations on top. These are called quasi-particles. And then you will find that this quasi-particle will move in the lattice, or in space-time. And you would realize that the quasi-particles which were in the system A, as soon as they leave A, the system is thermal. Okay, so it's a little bit classical physics. It's about particles moving. And then you can understand that the Mpemba effect, this is quite deep actually, the Mpemba effect is the possibility to create many excitations which are fast. That will give you this type of curve. So initially you have many excitations, but they are fast. And the green one will be what you need to observe a crossing. You are also able to create a cold initial state, so few excitations which are slow. And yeah, these quasi-particles have also been observed in a different scenario. So this was a very convincing, for me, explanation of the quantum Mpemba effect. It's not the full story, but there was some progress. So to conclude, it was an interesting journey going from classical to quantum and back, and also from theory, from experiment to theory. then theory classical convinced us to do theory quantum, and then theory quantum ended up with quantum experiment. So that's what I like. It's not about just classical and quantum, it's also about theory and experiment. Some questions about Mpemba remain open, I think most of them actually, because water is very different from trapped ions. But it's an interesting field of research, and in this quest of trying to find toy models and simple experiments, I think we make progress in combining all these tools where you have people from different fields. In my case, it was me, the quantum optics guy, talking with my collaborators to people from CISA, and then discussing with the experimentalists. I think this is how it should work to make it entertaining and hopefully meaningful. So thank you.